In this second part of depth perception, I'm planning to get through the binocular cues to depth perception, and then I think I'm going to stop. Just a reminder that the binocular cues to depth perception is the depth information that requires both eyes, so bi meaning two and ocular meaning eyes. So I've put this picture in here again to not lose the fact that this is when I'm looking at the tree in front of, and the tree is in front of the house. This is hitting the retina at T prime and H prime. I think there's little primes on there that is really, we're getting a two-dimensional picture. But remember, we have two eyes, so we're getting two pictures. And those two eyes are about 6 centimeters apart on the face, and so we're getting this disparity between the two retinas. There are differences, slight differences in those two pictures that give us this rich stereoscopic depth perception. And we're going to be examining the relationship between disparity and then what observers perceive, because it is the successful merging of those two images from those two retinas that's going to lead to this stereoscopic depth perception. So if we think back to that stroboscope that Max Wertheimer bought in the train station, another thing that really entertained people back before we had very much about moving pictures or anything was the stereoscope. And Charles Wheatstone in the 1800s was the one who created the stereoscope. This is somewhat related to viewmasters, although viewmasters are simple plastic examples of stereoscopes with really sometimes cartoons or whatever, where they're showing two slightly different pictures from basically with pictures taken as if they were 6 centimeters away. As the stereoscope, actually what they did was they would take two pictures 6 centimeters away from each other, and then you would put this stereoscope on your face and you would look at the two pictures with the left one going to the left eye, the right image going to the right eye, and then as you kind of brought those together and they merged, you would get this rich stereoscopic depth perception of some very nice pictures. Back when people used these, they were basically excellent photographers a lot of the times, using these cameras to create these stereoscopic images. The picture below, you can use this. So if this is on your screen, and you can pause it or stop it or whatever you want to do, if you go and get an index card or something so that you are making sure that the left image is going to the left eye and the right image is going to the right eye, you can see that it gives this rich stereoscopic view. And this is more like the Viewmaster, because they were really simple kind of images that weren't all that interesting. You can tell some differences here where the cactus on the left has a slightly different relationship with that window. Those are the kinds of slight differences that we're going to see from our two eyes. You can also do this if you move your index card between those two things that kind of look like stair steps. It works for those as well, where they become these kind of stair steps that are three-dimensional appearing and kind of moving. They're kind of oblique in depth. This is also what's happening with 3D movies. So it used to be that there would be film, and it would be done through a red filter, and then there would be a film from 6 centimeters away, right? And it would be done through a green filter, and you'd have to wear these goofy red and green glasses, and it had this kind of red and green appearance to it. They weren't great, but now what they do with the new 3D movies is there is a left, so one of the films is with a vertical polarity, and the other one is done with a horizontal polarity, and you put on the glasses and it's a lot more seamless than the kind of goofy old red and green filters. Another way to get this idea of how we really have two different images on the two different eyes is to take your thumb out at arm's length and occlude a particular object. So pick something that your thumb completely occludes. And when I do this in class, I kind of get really goofy with it and get to the kids in the hall, you know, where he would put his thumb up and close your right eye, and he'd say, I'm blocking your face out. I'm blocking out your face. And so I'm going to block out this plant with my right eye closed and my left eye open. And then you switch eyes. So you close your left eye and open your right eye. And what happens is your thumb is moved over, right, your thumb is moved over to the left of whatever object you were occluding. So again, the two different eyes are getting two different pictures. If we look at what's happening with that, so if we kind of use the near finger, you can actually do this with putting a finger out farther than the near finger and blocking it out. Again, closing your right eye, left eye open, have your near finger or your thumb have a far finger and block it out completely with your thumb that's closer. And then, so what's happening is you are getting that left eye so that it's in line, and the near finger is blocking out the near finger is blocking out the far finger. Then you switch eyes, and you blocking off the left eye, and that right eye, of course, the far finger is right in view, and the near finger is just over to the left. Some important terminology for understanding retinal disparity, sometimes called binocular disparity. They're just the differences between the two eyes, again, or the differences between the two retinas, is that there are corresponding points, so places on the retina that if we took one retina out of your eye and then slid it over top of the other retina, they would be on the same place. Okay, they would be landing on each other. They're basically landing on what I'm going to call now the horopter, which I'm going to describe in a second. And there are also non-corresponding points, which have some angle of disparity. So if I take the one retina, slide it over the other, they're not landing on the same place. And in fact, from that horopter and that place where they're overlapping, they have a particular angle of disparity or a particular angle of difference. And I continue to use an old picture from the book because I got really used to talking from it. He has a new picture, and if you find that more helpful, I think it's good to have two different examples. And so he'll be talk about a different example from how Goldstein talks about things, and I'll talk about this example. So the horopter is basically an imaginary surface that passes through our point of fixation. So when we are foveating on something and getting that on our foveal retina, those land on the horopter. Those are landing on the same places on the two retinas if we took those retinas and overlapped them and put them over each other. But also this kind of imaginary surface that is rounded like the retina, right? As we have this kind of rounded retina, and that horopter is indicating the objects that fall on the corresponding points of the two retinas. And he has a nice picture there of how, if he's looking at Frida, he has purposefully put Susan and Harry at places where they're going to nicely land on that horopter. So the two retinas, Susan, Frida, and Harry, are all landing on the same places or on corresponding points. Carol has some angle of disparity because she's not landing on that horopter. She's on a those two retinas are going to have non-corresponding points for Carol. And he starts by talking about absolute disparity. So this tells us how far the object is from the horopter. Carol, in this example, these are all really made up numbers, but she's going to have an absolute disparity of 26 degrees, let's say. And just remember that what we're doing is this kind of, it's this rounded, so we have how many degrees do we have around from our eyes? About 180, I think it's more like 190 degrees. We have these retinas back there that are about 190 degrees of a circle. And so she's going to be 26 degrees off from those 2 points that are non-corresponding are going to be 26 degrees different, if you will. If she starts swimming towards the lifeguard, her absolute disparity is going to increase. If she starts swimming towards Frida, her absolute disparity is going to decrease. So the absolute disparity of a particular object, that's going to change every time we change our point of fixation. Remember, we make about 3 fixations per second. So the question is, are we recalculating every time? Well, I'm going to say yes and no. Mostly no. No, because one, these are not calculations really. They are different neurons firing. But no, because we also have this relative disparity. So the disparities between the objects are going to remain constant as long as those objects don't move. So I put the picture back in here. If I'm looking at Frida and Carol is 26 degrees absolute disparity off of my corresponding, so not her non-corresponding points are, she's 26 degrees different on the two retinas. I changed my point of fixation as the lifeguard to look at Carol, and now Frida is 26 degrees. She has 26 degrees absolute disparity. Carol's on my horopter. She has changed to be basically 0 degrees of absolute disparity because she's on the horopter. But their relative disparity, they're still 26 degrees basically different from each other in that example. Okay, and some of the evidence about how binocular disparity is really creating this stereopsis, this really rich sense of depth perception. So if you again take the index card and put it between the two pictures on the left, you can see that there are differences. We can see that there are differences, and when you put the index card there, it gives you this rich stereopsis. Well, people would say, yes, but there are also all of these cues, right? I mean, even though we feel this kind of sense of stereopsis, people would argue, but the cactus in the front is in slightly different relationship with the window and with the bush behind it, and so forth and so on. And so in 1971, Bela Jules created these random dot stereograms. So if you take that same index card and put it between the weird random dot stereograms that are shown in A, you'll see this kind of little box pop out in that stereogram, okay? And what has happened here, so if you look at the, if I'm remembering it correctly, it's the zeros, the A's, and the X's are all black dots, let's say. The ones, the B's, and the Y's are all white dots, let's say. Don't think this really matches up with the stereogram above it, but that's okay. If we look at what's going on in B, we have this box in the middle that is AABB, that box. If you look over at what's on the right-hand image, that AABB, that box is shifted over one, right? Because now we have a YXXY, and we've basically deleted a different part of the scene, accreted a different part of the scene, and what's landing on that right eye is different. And actually, you can watch that AABB box also pop out in depth. And so these random dot stereograms suggested, yes, this is truly binocular disparity that is creating this rich sense of stereopsis. And here I have one of those magic eyes. So this is a random dot stereogram. And if you can figure out how to look at it, you will see, I think it's kind of a water creature pop out. And so at different points in my life, so most of my life, I've never, ever, ever gotten these to work. And then I had this, one day I was getting ready for this class, and I had this Tool album. I don't know if you guys know Tool, or really it was a CD. And they have these these separated eyepieces so that it is making you look at the pictures in a certain way. And they had two pictures, and you would put them together in this kind of rich sense of depth, and it's all set up for you to do that. And somehow that had trained my eyes to do this. I mean, I think this was fall of 2019, so I was 49 years old, never gotten these to work ever before. These were very popular in the 90s when I took this class, never got a single one to work. And finally, I got this one to work after looking through that eyepiece. And so if you kind of do this practicing, if you've never seen these, if you kind of do that practicing with the index cards, and then just kind of train your eyes of what you need to, how you need to separate your vision, because usually what's happening is our two eyes are working together, and the musculature is such that they are focusing on a scene in a certain way. And it's just, you have to kind of have to look either behind or in front of, and you can kind of put your finger behind and make yourself look at that finger behind it, and then it pops out. And it's this kind of weird, I don't know, sea creature thing that's popping out. And it's really cool. I got really excited about it before that class. One of the problems or the questions that we have when we are trying to explain depth perception is the correspondence problem. How does the visual system match the pieces of the image on the left eye that correspond with the same pieces of the image that land on the right eye? Well, again, with these kind of realistic examples, green goes with green. We're really kind of putting that together. We have a lot of explanation for maybe how this happens in the real world, but go back to the Bailey-Jules random dot stereogram. That's not helping us there. Those other visual cues are not there in those random dot stereograms. And so these 4 different researchers that I have listed are from really wildly different fields. So I think one's mathematics, engineering, neuroscience. I can't remember the other one right now. So many different people from many different backgrounds are trying to explain the correspondence problem and how the visual system is solving this problem. And it doesn't sound like they really agree with each other. I haven't read all of these. They've kind of stayed on my summer reading list as kind of a really fascinating question that we don't necessarily have the answer to, since we're not agreeing about what that answer is.